In France, they're using this mobile 3D printer for building large concrete structures directly at the construction site. So instead of assembling prefabricated parts or using traditional formwork, it creates walls, columns, and other vertical elements by layering a concrete-like material with a robotic arm. It is capable of printing structures within an area of up to 12 by 12 by 7 meters and operates with a radial robotic arm that delivers layer-by-layer concrete construction directly on site. Its motion system allows nozzle speeds between 3.15 and 9.84 inches per second, and vertical build rates range from 11.8 to 23.6 inches per hour, depending on the material used. Layer thickness can reach a minimum of 0.2 inches, offering precision for large-scale components. The machine is compatible with pumpable concrete materials, including a proprietary mix intended for structural performance with a reduced environmental impact. It supports aggregate sizes up to 0.2 inches and allows the use of short fibers up to 1 inch in length. It operates through specialized slicing software compatible with STL and DXF files from common CAD tools like AutoCAD or Revit. Live monitoring includes a camera at the nozzle, built-in weather sensors, and real-time data tracking for pump performance. The system functions in ambient temperatures from 23 degrees Fahrenheit to 122 degrees Fahrenheit and can continue printing in wind speeds up to 37 miles per hour. Indeed, seems fine, but the promise of rapid deployment seems to apply mainly to the printer itself, not the overall job site, as it still will need a prepared, level foundation and access to power, water, and raw materials, right? Plus it works in a radial envelope, so the height for taller projects might be an issue too. Nampa, Idaho. And it really seems that in a controlled factory setting, robotic automation is reshaping how wall panels are assembled for modular construction. This system uses ABB industrial robotic arms equipped with vacuum lifters, adhesive applicators, vision cameras, and fastening tools to handle the entire process. Starting with pre-cut studs, plates, and sheathing panels, robots apply glue at specified points, position framing components into jigs, and secure them in place. Other robots then place sheathing panels, fasten them with nails or screws, and cut out precise openings for windows, doors, and electrical boxes. The equipment runs on data pulled directly from 3D models or BIM software. Design files are translated into machine instructions, guiding every robot through its tasks. Vision systems monitor alignment and placement in real time, allowing for quick corrections and high consistency. Finished wall panels are moved through the line and held in buffer zones before being sent to construction sites or assembled into full modules. This method addresses several persistent challenges in construction. It reduces the amount of material discarded during production, minimizes physical strain on workers by automating heavy and repetitive steps, and delivers higher output than traditional framing methods. ABB reports production speed improvements of up to 38% and a 30% drop in material waste during pilot projects. Other studies on automated lines suggest the system can produce dozens of wall panels per day under normal operating conditions. The system works best when wall panels follow standard dimensions and consistent layout logic, making it easier for the robots to perform their programmed roles. On-site work is still required to finish mechanical, electrical, and plumbing systems, but the majority of the structure is handled off-site. In Pennsylvania, they have this autonomous rebar tying robot named Tybot that ties rebar, reinforcing steel bars, on construction sites, especially in bridges and large concrete decks. It speeds up large construction projects, saves time, reduces physical strain on workers, and keeps the quality of the work consistent. Here's a simple explanation. When workers build a bridge or a large concrete floor, they first place a grid of steel bars to make the concrete strong. Normally, workers must tie the bars together by hand using wire. A slow, repetitive, and tiring job, but this machine does it automatically. mounted on a metal frame that moves across the grid of steel bars. It has cameras and sensors that let it see where the bars cross each other. When it finds an intersection, it quickly ties them with wire. More than 1,200 ties per hour. It doesn't even need digital maps or programming. Once it's set up on the deck, which takes about 2 hours, it starts scanning and tying automatically. It works day or night and in different weather conditions. The machine can cover areas from about 11 to 117 feet wide, and it ties bars up to number 8 by number 9 in size. Those are standard rebar thicknesses. It uses 15-pound spools of wire and can run for around 10 hours before refueling the generator. To us, it seems fine, but maybe only for larger projects, causing smaller pours, say 1 or 2 week jobs, the payback may be less compelling. In other words, on very small jobs, the setup overhead may reduce the robot's cost or productivity advantage. Plus, it doesn't work vertically yet, so for structures with heavily sloped, curved, or vertical rebar grids, or very irregular geometries, the machine will still rely on manual labor. Annyeonghasimnika in South Korea, and I promise it means hello. Integrated into the very fabric of a building's exterior, this solar solution replaces the conventional idea of rooftop panels with something more advanced. Building integrated photovoltaic modules. These aren't mounted on top, they are the roof and the facade. Using monocrystalline N-type silicon cells, the modules operate within a typical efficiency range of 19% to 22% based on comparable LG neon solar lines. The double-sided tempered glass construction adds structural integrity and fire resistance, while also allowing for colored finishes that adapt to architectural needs. They're built to endure harsh environments, with an operational temperature range from -40 degrees Fahrenheit to 194 degrees Fahrenheit, and front-rear mechanical load ratings of approximately 113 pounds per square foot. Though full technical specs for the ThinQ Home BiPV modules are not public, LG's other solar module lines help outline performance expectations. The system pairs with LG's Home 8 energy storage system, offering 15 kilowatt-hours usable capacity per unit and modular expansion up to around 58 kilowatt-hours. This setup is coordinated through the ThinQ energy platform, which enables AI-powered load scheduling, energy monitoring, EV charger integration, and grid interaction. This solution functions as both an energy generator and a part of the building's envelope, essentially a dual-purpose material. It aligns with South Korea's zero-energy building policies and is suited for buildings targeting net zero performance. On a systems level, it combines generation, storage, and intelligent control. Energy produced by the modules is stored and managed within the platform, which adjusts usage based on demand, weather, and user behavior. The platform supports backup power and allows interaction with grid services, making the system flexible and future-ready. And konnichiwa! We're here in Japan for ACETube, an autonomous haulage solution used in large-scale open-pit mining. It allows massive electric drive trucks, each capable of carrying between 220 and 440 tons of material, to operate without drivers. The vehicles move along predefined routes, controlled remotely through a central operations center. It gave us high-precision GPS navigation, onboard computers that handle steering, acceleration, and braking, as well as radar and laser sensors to detect any obstacles or vehicles on the route. It relied on wireless communication networks to maintain constant connection between trucks, support equipment, and the central control hub. Now, trucks operate continuously, day and night, without the need for driver shifts or rest periods. This consistency improves fuel use patterns and reduces wear on tires and brakes. The entire route network, loading zones, dump points, fueling areas, is mapped digitally to guide the autonomous vehicles. Technical specifications from one example truck included a gross vehicle weight of about 916,000 pounds, a payload capacity of around 507,000 pounds, and a power output of approximately 2,700 horsepower. The maximum speed reached nearly 40 miles per hour, with a turning radius of roughly 52 feet. Vehicles measure about 49 feet in length and 28 feet in width, using large, specialized tires. The system managed the entire truck fleet, not just individual vehicles, and is integrated with dispatch software to coordinate tasks, monitor conditions, and analyze performance. So all we could say was, "Kanpeki desu." It means perfect in Japanese. I hope that's what it means. Up further, we analyzed this luffing jib tower crane, towering over 720 feet. It lifted up to 220 tons and operated independently at heights over 720 feet in freestanding mode. At full capacity, it maintained a lift speed of around 20 feet per minute and offered fine control with micro-motion precision near 0.2 inches per second. Its load moment capability reached 3,300 ton-meters, providing the mechanical advantage needed for handling large-scale components at height. Speaking about a tower crane built to lift extremely heavy components to extreme heights used in the constructions like tall wind turbines, where large parts like nacelles, blades, and tower sections need to be positioned with high precision. The crane also functions effectively in locations where space and access are limited. Its footprint, about 98 by 213 feet, supports operation in narrow or remote environments such as deserts and hilly regions, where wind farms are commonly located. The structural system requires no permanent foundation and no external attachment during operation. It can be broken down into modular sections, which allows easier transport and reassembly between turbine positions, a key factor for large-scale projects involving dozens of towers. Performance in high wind areas is supported by stability features that allow continued lifting in conditions up to wind level 6 and safe standing during level 10 winds when not in use. These capabilities help reduce downtime in areas prone to changing weather. Meanwhile in Taiwan, so one and everyone. And this is a large fabric tube, used to separate water from mixtures like sludge, sediment, or slurry. It's made from woven synthetic fabric, usually polypropylene, or PET, that lets water pass through while trapping solids inside. The fabric is strong, resistant to sunlight, chemicals, and biological decay, and holds up well in wet environments. The tube works by pumping the wet material into it. As the tube fills, water filters out through the fabric and the solids stay inside. Over time, the contents settle and dry, reducing in volume. The solids can later be removed, repurposed, or disposed of. The system can be made in different sizes, depending on the needs of the project. For example, one tube used in a sludge project measured 69 feet around and 98 feet long. Its volume capacity can exceed 1,700 cubic yards. Much more than a traditional drying bed. The fabric is engineered to strike a balance between drainage and solid retention, allowing fine particles to stay in while water exits. Openings in the textile are small enough to prevent material loss, but large enough to support fast drainage. In some cases, additives like polymers are used to help the particles settle more quickly. This setup is used in places like harbors, mining sites, and farms to manage sediment or waste efficiently. It handles large volumes and can be placed in various types of prepared ground or containment zones depending on site needs. Further Canada! In a precise 3-day lifting sequence, a 30,000 square foot concrete structure rose into place through the tilt-up construction method. The building is composed of 25 site-cast concrete wall panels, totaling 17,371 square feet of surface area. The largest panel measures about 856 square feet, the tallest reaches 28 feet, and the heaviest weighs around 73,500 pounds. All panels were prepared and cast directly on the site floor slab before being tilted upright with a crane. The project included both insulated and non-insulated panels, with the insulated portion covering the full perimeter to achieve stable thermal performance. Tilt-up construction operates by forming each concrete wall horizontally on a flat surface. Reinforcing steel bars are placed within the formwork, along with inserts for lifting and permanent connections. Once the concrete has cured, the crane raises each panel to a vertical position and places it onto its footing. Temporary steel braces keep the walls in place until the roof framing is attached and the building becomes self-supporting. This method allows large wall sections to include window and door openings, architectural grooves, and insulation layers during casting, eliminating the need for external fabrication or long-distance transport. Each panel carries both structural and thermal functions. The reinforcement grid controls cracking and supports loads from wind and seismic forces. Insulated panels use a sandwich system of concrete, rigid insulation, and another concrete layer, creating continuous insulation across the wall without thermal breaks. Embedded plates and connectors provide precise alignment during assembly and secure attachment to the roof and floor systems. The entire lifting operation was completed within 3 days, demonstrating a coordinated workflow and high productivity. And then, in Italy, they use this modular formwork system to create an empty space beneath concrete slabs and foundations. It also provides a route for mechanical, electrical, or plumbing lines. It consists of plastic base plates, vertical plastic pipes, and top modules that lock together to form a grid. Once assembled, concrete is poured over the structure, creating a solid, reinforced slab that rests on the vertical supports. The space underneath remains open. The materials include about 97 to 99% recycled polypropylene for the formwork, and a mix of PVC and calcium carbonate for the pipes. So that air gap beneath the slab remains ventilated, and that gap helps reduce soil gas buildup, allow airflow, and separate the concrete from cold or damp ground. The structure can support loads up to roughly 20,480 pounds per square yard, depending on how thick the concrete slab is and how it's reinforced. The main components include square base plates and domes, each about 22.8 by 22.8 inches. The height of the void can range from approximately 28 inches up to 118 inches, depending on how long the vertical pipes are cut. The pipes are 5 inches in diameter and support the slab above. This setup replaces traditional fill methods, requires no special equipment, and is installed by hand before pouring concrete. It is used in both residential and industrial construction where a ventilated or raised foundation is needed. Seems quite promising, but this method may reduce shear strength, lower stiffness than solid slabs, higher initial cost, certainly takes more time, and depends heavily on precise design and installation to perform as intended. Gwitch. In Ireland, there we analyze this modular arch bridge system made from precast concrete blocks. Each block, called a voussoir, is joined with a flexible layer that supports them during transport and installation. Once in place and filled with material like gravel or concrete, the arch acts as a single structure, carrying loads through compression, similar to traditional stone arches. The system doesn't need complex temporary supports during construction. Instead, it can be delivered in flat sections, assembled quickly on-site, and backfilled in a single day. The result is a bridge that combines modern construction methods with the load-bearing principles of masonry arches. Adding to this that this setup supports installation in new builds and upgrades to existing structures. The concrete used in the arch blocks typically reaches strengths of around 50 megapascals, supporting long-term use with minimal material degradation. Tests show the structure can carry loads up to 74 tons once assembled and filled. Span sizes tested at approximately 16 to 49 feet wide and up to 10 feet high. As for our thoughts, the system's limitations include untested performance under foundation scour, maybe the sensitivity to backfill quality, and the need for heavy lifting equipment due to the high weight of individual arch units. Plus, there's limited public data on dynamic or seismic loads. And in US, there's this high-output machine used to manufacture round concrete pipes using a bidirectional roller head system. It covers pipe diameters from 8 to 84 inches and lengths up to 12 feet, depending on the model selected. A36, A48, A84, etc. The system's core mechanism drives the roller head in both directions, which improves concrete compaction and helps produce consistent pipe surfaces. It includes a revised drivetrain with 6-inch chrome guide tubes and PTFE bearings, contributing to stability during operation and reducing internal wear. The top table now moves independently of the crosshead, which shortens drop time and helps increase. The turntable's reduced diameter allows faster rotation, and its two-piece design supports drop-in bottom centering plates for better alignment during setup. The optional Edge automation platform uses an Allen Bradley PLC and HMI interface, giving operators access to production data remotely. The material hopper keeps a continuous flow with air vibrators, dual gates, and a sensor system in the Edge variant to detect loss of feed. Main motor output on the crosshead reaches 200 horsepower at 3,600 RPM. The hydraulic unit supports 60 horsepower with a tank volume of about 200 gallons. Packer shaft speeds vary from 75 to 375 ARPM, based on earlier specifications. Hopper volume measures around 4.6 cubic yards, allowing steady material input during production. There are a few things to keep in mind though. Example installation requires a substantial pit foundation, including power and hydraulics. Changeovers and mold, window or tooling compatibility must be managed carefully. And choosing the correct model size is important to avoid under or over capacity. Next, in England, they have this 8-meter electric Bumpa, a machine that helps move building materials like roof tiles, bricks, and tools from the ground up to higher levels, such as scaffolding or rooftops. Speaking about 1,000 roof tiles in just 25 minutes. How about that? It reaches up to about 23 feet and uses a belt system powered by a 110-volt electric motor. The belt moves at around 66 feet per minute, and the hoist can carry up to 176 pounds in total, though each individual load on the belt should be no more than 44 pounds. To use it, workers set it up at an angle against a building or scaffold. Materials are loaded onto the belt at ground level, then carried up to where the work is happening. If any materials need to be brought back down, it works in reverse just as fine. This feature helps reduce trips up and down ladders or scaffolding, which can save time and effort. Setting it up takes a bit of planning. It needs to be placed securely, the angle adjusted properly, and the power supply connected safely. It's usually a two-person job to position it, though using lifting equipment might make it easier. The hoist is controlled by a handheld remote, so the person operating it doesn't have to be right next to the machine the whole time. As per our thoughts, it does make some noise though. Over 75 decibels precisely, so ear protection might be worth considering. In Poland, they say Dzień dobry in Poland, and there they're using a modular building system made up of prefabricated units, or modules, that are constructed in a factory and then transported to a construction site. These modules are built to connect side by side or stack up to form complete structures, such as homes, offices, or apartment buildings. Each module is self-supporting and strong enough to handle transportation and lifting by crane. In a typical example, 3 modules combine to form a 2-story building measuring about 12 feet in width, 38 feet in length, and offering around 1,000 square feet of usable space. The factory production process includes electrical, plumbing, and climate systems, which are mostly installed before the modules leave the facility. Up to 95% of the building work is completed in the factory. While the modules are being made, groundwork like foundations and utility connections can be done on-site. Once the modules arrive, they are placed and connected quickly, which helps reduce overall construction time by as much as 70% compared to traditional methods. An online tool is available to customize building layouts, allowing selection of roof type, number of stories, module grid, and overall size. The system also supports energy-efficient features such as integrated solar panels, battery storage, and smart control systems for building performance. Overall seems okay, but this method might bring troubles with transportation. Moving large, fully built modules requires special logistics, which can increase costs, limit design dimensions, and complicate delivery depending on the location. Ahoy! In Czech Republic, arched steel buildings use a smart construction method where the curved steel ribs form both the structure and the outside shell. There's no real limit on how long the building can be. It can keep going as long as needed by adding more sections. One big advantage is that the weight of the building spreads evenly along the ground, which makes the foundation simpler. Often, a concrete strip or a flat base like asphalt is enough. Once the base is ready, steel coil is fed into a forming machine that curves it into shape. These ribs are then lifted and connected to form the full arch. Straight steel pieces are used at the ends of the building, and doors, windows, or light panels can be added there. For airflow and daylight, there are options like roof vents or skylights. Insulation can be included using thick layers of mineral or basalt wool to help control temperature inside. These buildings go up fast. Say a 5,400 square foot hall can be finished in just a few days, and even larger ones in under a week. They also cost much less than brick or traditional steel buildings. With the right materials, they last for many years and don't need much maintenance. To us, this technology, by the way, is called K-span, while efficient, can face challenges, including complex structural analysis due to non-standard curved profiles, vulnerability under extreme snow or wind loads, dependency on skilled labor and proper equipment for assembly, and even potential transport or handling issues with larger spans or unusual site conditions. So, yes. Next. Namaste from India, and looking at a robotic machine as it navigates construction floors, laying blocks in sequence with minimal human input, on a pace roughly 10 times faster than conventional masonry methods. You can move it across standard building floors and pass through doorways quite easily, and it automates the wall building process using common block types, including larger formats up to 24 inches. And its operation is based on data received from the project's digital layout. It applies cement mortar and places each block in position, following digital building drawings that guide its movements and account for wall features like windows and doors. Each step of the process is tracked, producing block-level information useful for monitoring progress, planning material supply, and reviewing construction stages. This type of system responds to key demands in construction, particularly where skilled labor is limited and timelines are tight. For building teams already working with digital plans and block-based designs, it fits within a workflow that favors pre-planning and layout consistency. Tasks such as detailing, joint finishing, and non-standard features still require manual work, but for wall assembly itself, the machine offers a repeatable and measurable approach to construction. We observed the system working in real construction environments, placing blocks efficiently, and adjusting to the wall blueprint, which removes the need to pause for each wall opening. And it seemed like was capable of anything a site worker is, except for whistling at women passing. Just kidding, of course. To us, this machine might struggle with complex layouts, needs well-prepared sites, and may offer limited cost benefits on smaller or non-standard projects. Further, we're in UK. They have this material, which is a type of concrete that includes added fibers to improve its durability through three-dimensional reinforcement. Instead of relying only on traditional steel bars or mesh, this concrete mix contains tiny fibers, either synthetic or steel, that are spread evenly throughout. These fibers help hold the concrete together once it starts to crack, improving how it behaves under stress. The fibers come in different types and sizes, depending on what the concrete is being used for. Synthetic fibers are often about 2 inches long and made from polymer materials, with tensile strength around 65,000 pounds per square inch. Steel fibers are also around 2 inches in length, but have higher tensile strength, reaching up to 210,000 pounds per square inch. The dosage range typically falls between 34 and 67 pounds per cubic yard, depending on the load-bearing requirement. These fibers don't increase the initial strength of the concrete, but become active once cracks form, controlling their spread and helping the structure keep its shape and function. The amount of fiber added depends on the project, ranging from about 5 to 10 pounds per cubic yard for synthetic fibers and up to 67 pounds per cubic yard for steel fibers. As an opinion, I don't know how they manage fibers that may stick out from the surface after finishing. Does that mean extra time for smoothing? Plus, as long as I am concerned, in environments with high chloride exposure like marine settings, steel fibers may corrode over time, which can cause staining or long-term durability concerns, even though they are often less exposed than traditional steel reinforcement. Grußgott, Austria. Concrete structures can be formed using a method where the mold continuously moves upward while the concrete is placed. This process is called slipform construction. In this system, aluminum panels are used to shape the walls, and their contact surfaces are covered with stainless steel. The result is a solid, uninterrupted structure shaped in one upward movement. The stainless steel lining also helps maintain dimensional precision during repeated use. This system is modular, fitting different floor plans and structure types. It is often applied to vertical elements such as lift shafts, stair enclosures, and high retaining walls. These panels are attached to a support framework that includes hydraulic jacks, which gradually lift the formwork as the concrete hardens. Platforms for workers move along with the form, giving constant access for reinforcing steel placement, alignment checks, and finish control. Construction starts with the assembly of formwork on a base slab. Once reinforcement is in place, concrete is poured to an initial height. After it gains early strength, the formwork begins to move upward at a pace matched to the hardening rate of the concrete. The process continues in a continuous vertical progression, which reduces construction time by avoiding stops between sections. Embedded items, like service boxes and openings, can be integrated using aluminum inserts that fit into the panel layout. The concrete surface formed through this method is uniform and joint-free, which increases structural performance over time. Since the form does not need to be taken apart and reassembled between stages, the overall work sequence becomes more efficient. Guten Morgen in Germany. Looking at a tunnel boring machine, an advanced piece of excavation equipment designed to dig through soil and rock while simultaneously constructing the tunnel lining behind it. It is used on the high-speed rail project between London and the West Midlands, represents some of the largest and most technically specialized in operation today. Each of the main machines, including Florence and Cecilia, measures roughly 558 feet long and weighs about 2,200 short tons. They feature a rotating cutter head with a diameter of 33 feet, powered by motors delivering up to 5,000 horsepower and torque of around 12 million pound-inches. These specifications allow the TBMS to handle complex geological conditions, particularly the chalk and flint of the Chiltern Hills. Excavated material is removed via conveyors or pipelines, and precast concrete lining is installed in rings behind the cutter head and sealed with grout. These machines can advance about 50 feet per day, launched from shafts as deep as 72 feet. TBMs on HS2 vary in diameter from 28 to 33 feet and are customized for local ground conditions. In the Chiltern Tunnel alone, they placed over 56,000 segments per tunnel and handled about 2.6 million cubic yards of spoil. Their precision and ability to operate continuously enhance safety and reduce timelines. TBMS, also limit surface disruption, making them essential to building high-speed rail infrastructure efficiently and sustainably. Again in Germany, and there's this jet grouting, the specialized method for improving soil conditions underground, using high-pressure jets to break up and mix the soil with a cement-based grout. The process forms in-place soil cement columns with specific strength and permeability characteristics, often used where structural support or water sealing is required. Technically, it achieves drill depths up to 131 feet and column widths between 2 to 10 feet, depending on ground conditions and tooling. Pressures involved range from 5,000 to 9,000 psi. The hardened columns offer compressive strength levels from 290 to 1,500 pounds per square inch, while their permeability can be as low as 10 to the -9th meters per second, meeting demanding geotechnical needs. Equipment used for jet grouting varies in size, from compact setups to large rigs weighing around 66,000 pounds. The method starts with a borehole drilled to the planned depth. Once at depth, high-energy fluid jets activate, breaking apart the surrounding soil while injecting grout into the loosened zone. As the drill string is slowly withdrawn and rotated, a cylindrical body of soil and grout forms, which hardens over time. This results in improved soil behavior without needing excavation or removal of existing material. Jet grouting is especially relevant in locations where structural elements must be stabilized below ground level, or where water needs to be blocked, such as underneath slabs, around tunnels, or at foundation bases. It has been used for foundation reinforcement, excavation support, and constructing cut-off barriers that limit fluid migration. Though it involves advanced equipment and careful engineering, jet grouting enables precise control over underground soil performance and structure interaction. To us, it remains an important option in projects where conventional methods cannot meet performance or spatial constraints. Gruisch Sack, Greisax, Switzerland. This is a professional survey drone with a wingspan of about 4.1 feet and a total takeoff weight of around 11 pounds. It can carry payloads up to 2.7 pounds and uses 2 lithium polymer batteries for power. Its main communication range extends up to 6 miles, with an optional cellular connection for extended missions. It lifts off like a quadcopter and then transitions into forward motion, allowing it to cover wide areas in less time than typical drones. Its configuration is known as a tail-sitter VTOL, enabling it to operate in confined spaces without the need for a runway. The drone has a flight speeds can reach up to 49 miles per hour, and it performs reliably in wind conditions up to 27 miles per hour. A launch and landing area of around 6.5 by 6.5 feet is usually sufficient. As a key feature, they see its ability to swap payloads without tools. These include high-resolution RGB cameras, up to 61 megapixels, multispectral sensors, telephoto lenses, and LiDAR scanners. Depending on the sensor, the drone can achieve ground resolution as fine as 0.2 centimeters per pixel and map up to 1,360 acres in one flight. It supports high-precision GNSS post-processing for sub-inch horizontal accuracy without needing multiple ground control points. Obstacle sensors, geofencing, and a dual battery system add safety and stability. The drone is intended for use in mapping, inspection, and environmental data collection tasks that demand accuracy and scale. Is it just me, or it's a bit too fast for certain detailed inspection work? Goedenavond, Netherlands. There's this interesting material, a type of concrete that can repair its own small cracks without human intervention. It uses a special mix that includes bacteria spores, nutrients, and a mineral-based carrier. These components are blended into fresh concrete or used in repair mixtures for existing structures. The bacteria inside remain inactive until a crack forms and both air and water enter the damaged area. Once triggered, the bacteria feed on the nutrient and produce calcium carbonate, a mineral similar to limestone, which fills and seals the crack from the inside. This process helps prevent further damage and extends the material's usable life. It can close cracks up to about 1 millimeter wide on its own. There are a few forms available: an admixture added to fresh concrete during mixing, a one-component cement-based mortar used for surface repairs, and a liquid version for injecting into existing cracks. This self-repair system does not change how the concrete sets or gains strength during curing. It functions in structural parts such as walls, floors, and foundations, particularly in areas where keeping water out is important. While the healing reaction only begins when air and water reach the crack, the material can reduce long-term maintenance and repair work. In some cases, it may even allow engineers to use less steel reinforcement because the concrete itself helps keep cracks under control. Next, we were in Portland to see an augmented reality platform used on construction sites to view 3D building models directly overlaid onto the real environment. It works by taking models from widely used design software and converting them into a lightweight format that can be viewed through AR headsets, or in some cases, mobile devices. The system lets users walk through a construction site while seeing full-scale digital models aligned with the physical space around them. The AR display uses a wireframe or edge overlay to make sure users can still see their surroundings clearly. The model can be aligned on-site in a few steps without needing complex setup, using visual markers or QR codes when necessary. The alignment system includes rotation, location, and fine-tuning through anchors. Models are stored on the device, allowing use even when there's no Wi-Fi or internet connection. Different layers of the model, such as plumbing, structural, or electrical systems, can be turned on or off. Users can also access details about components by selecting them within the AR view. The system supports capturing observations, photos, and notes, which are tied to specific locations in the model. These can be used for inspection, verification, or coordination with other teams. It supports large models by compressing them into a format optimized for performance. And our thoughts on where just, oh wow. Doesn't this remind you Iron Man using augmented reality holograms to walk around, inspect, and modify 3D models of his suits, buildings, and tech in his workshop? And ni hao here in China. We see this prefabricated steel structure used as a hangar or large industrial building. They measure approximately 195 feet in length, 64 feet in width, and 28 feet in height, cover around 12,735 square feet, and use about 92,000 pounds of structural steel. It handles wind speeds up to 89 miles per hour and meets seismic conditions up to magnitude 7. It's made primarily from strong, factory-produced steel components that are delivered in parts and assembled on-site. The building is designed to cover a large, open space without needing interior columns, making it suitable for housing aircraft, machinery, or equipment that requires clear movement space. The frame is made from structural steel sections, mainly hot-rolled or welded H-shaped beams with high yield strength. Secondary components, like purlins and bracing, are made from slightly lower grade steel. Roof and wall panels are either single-layer corrugated steel or insulated sandwich panels, depending on the needs of the space. These panels can range from about 2 to 6 inches thick. Steel members are treated with either paint or galvanization to resist wear from exposure. Assembly is done using pre-cut, pre-drilled steel parts and high-strength bolts, which speeds up construction and increases accuracy. This type of building is typically used in aviation, manufacturing, logistics, or storage, where open interior space is important. To me, steel structure hangars offer wide open spans and fast assembly, but they can face issues like rust in humid environments, poor insulation without upgrades, and reduced strength in high heat unless fire protection is added. So, yeah. Next in Washington, there's this project that of a large educational campus built using a construction method called cross-laminated timber, CLT, a type of engineered wood. CLT is made by stacking layers of lumber at right angles and bonding them together to form large, solid panels. The campus includes 2 connected school buildings, both 2 stories tall. The structure uses approximately 203,000 square feet of CLT for its flooring and roofing systems. The panels are supported by glue-laminated timber beams, with exterior and interior walls made from a mix of tilt-up concrete and wood framing. CLT panels are strong in multiple directions due to their cross-layered design. They are pre-cut and pre-drilled off-site, which helps speed up installation and reduces material waste. In this project, more than 800 uniquely shaped panels were installed, some spanning long distances between beams or walls. The design leaves much of the wood surface visible inside the buildings, creating a warm, natural appearance. Technically, the structure is classified as Type 5B construction and meets fire and structural safety standards. Although specific panel thicknesses are not listed, similar systems typically use panels with 5 to 9 layers, depending on the span. The use of mass timber in this project reflected a move toward modern wood construction methods that offer structural performance, efficient installation, and a distinct visual style. Now we know that a composite reinforcement method is changing how concrete structures are strengthened and repaired. So again with fibers, and this time in US. Speaking about carbon fiber fabrics or strips combined with a resin system, creating an external layer that works together with the existing concrete to improve its structural behavior. Americans are using these fibers in buildings, bridges, marine structures, and other infrastructure projects with a tensile strengths between 3,000 and 6,000 megapascals and stiffness values of 230 to 350 gigapascals. Elongation at break generally falls between 1% and 2%, while the resin, often an epoxy, offers tensile strength of 40 to 80 megapascals and a modulus of 2 to 4 gigapascals. Cure time depends on temperature, usually ranging from 24 to 48 hours. This method can increase flexural strength by 20% to 100%, and shear strength by 30% to 60%, depending on the original structure. When wrapped around columns, the carbon fiber wrap improves confinement and ductility, especially important in seismic zones. The system also helps control cracking, which can extend the life of the structure. Installation begins by cleaning and preparing the surface, filling cracks, and grinding or blasting the area down to solid concrete. A primer is applied to create a strong bond. The carbon fiber strips or fabric are cut to size, positioned on the surface, or wrapped around structural elements like columns, then saturated with resin to create a continuous bond. After curing, the result is a new external reinforcement that significantly increases the member's capacity. So, just wow! isiZulu from South Africa. I've been told that this means hello, so let's hope for the best. We analyzed this yellow machine, and is a heavy-duty articulated dump truck used for hauling large loads in mining, construction, and earth-moving environments. Mining? South Africa? What does that remind you? Its power output ranges from 210 kilowatts to 430 kilowatts, depending on the model. Torque on smaller models reaches 1,150 Newton meters at 1,200 to 1,600 revolutions per minute. Transmissions are fully automatic, offering 6 or 7 forward gears with torque converter lockup. Fuel tanks hold up to 79.8 US gallons, and additional 9 US gal AdBlue tanks support emissions control. Tires are typically 23R, 25 radial types. Dump body volumes reach approximately 19 cubic yards, with programmable tip angles near 70 degrees. Its fully loaded weight can exceed 121 pounds. This type of truck features an articulated steering frame and central oscillating joint, allowing flexible movement across soft or shifting ground. high flotation tires, combined with automatic traction control and electronically managed differential locks, improve stability and handling during transport. Next, we're in Italy analyzing a bathroom system, but I don't feel like saying, "Ciao, don't know why." We throw a dice, and it landed in a fully assembled bathroom unit made off-site and delivered as a single module to be installed directly into a building. It arrives with all the internal systems already in place, such as plumbing, electrical wiring, drainage, tiling, lighting, and fixtures, so it only needs to be connected to the building's utilities once on-site. There are two main construction types. One uses a galvanized steel frame combined with composite panels, forming walls that are about 3 inches thick. The other is made entirely from lightweight concrete, with walls and floors approximately 2 inches thick. Both versions are finished with a layer of ceramic tiles around 0.4 inches thick. In the concrete model, the entire shell is reinforced with steel mesh to provide additional strength. Floor structures can be very slim, starting at just under half an inch, or made from a concrete base that's 2 inches thick before tiling. Materials used in both versions are selected for their strength and resistance to water. These bathroom units are typically used in buildings with many repeated layouts, such as hotels, apartment complexes, hospitals, or dormitories, where consistent quality and fast installation are important. Each unit is designed to fit the space exactly and can be finished with different styles, fixtures, and layouts depending on project needs. Because they are built in a controlled factory setting, these units allow for more accurate construction and quicker installation compared to building bathrooms on site from scratch. In Germany, they showed a hydraulically operated self-climbing platform used for constructing concrete cores in tall buildings. It moves upward as a single unit, lifting not just the formwork, but also the working platforms and any attached equipment in one continuous motion, without needing a crane for each repositioning. It's made to handle tall, reinforced concrete walls, like elevator shafts and structural cores. The system operates using hydraulic cylinders, each capable of lifting up to 40 metric tons. It can rise nearly 16 feet in a single lift, and a full lift cycle typically takes about 20 minutes for one floor level. Wall heights supported range from approximately 9 to 16 feet. The platform comes with large working areas that allow space for materials, rebar, and concrete placing booms. This setup enables workers to pour slabs and walls during the same cycle, which can speed up construction. Up next in Norway, this is a type of concrete roof tile used to cover and protect sloped roofs. It has an S-shaped curved profile that helps guide rainwater off the roof and gives it a smooth, structured look. Made from molded concrete, it's built for use in climates with changing weather and is commonly used in both new buildings and roof renovations. The tile measures about 16 inches in length and 13 inches in nominal width, with a coverage width of roughly 12 inches. Each tile weighs approximately 10 pounds, and you'll need around 10 tiles to cover 1 square meter of roof area. It can be installed on roofs with a slope as low as 15 degrees, as long as the rest of the roof system supports it properly. The tile has a special surface treatment that reduces the growth of algae and helps protect it from sunlight. Color options often include black, red, clay red, and grey, allowing for some variety in appearance. As for the thoughts, I don't know. The weight. Isn't that a bit heavy for a roof tile? Plus, on very shallow roof slopes, water shedding may be compromised. i.e., if the slope is below the manufacturer's recommended minimum, risk of leaking may go up. Did anyone use so far? Dewatering. Here in Poland, looking at this modular construction system designed to deliver fully formed building units that arrive on site with up to 95% of the work already completed. The structure uses a steel frame and composite envelope with carefully layered insulation and finishes, engineered for high energy performance and environmental resilience. Module sizes typically span 10 to 13 feet in width and up to 49 feet in length. That matches standard transport dimensions. Say a 2-story setup, for example, can cover over 1,000 square feet of usable space. Each module includes pre-installed mechanical, electrical, and plumbing systems, along with interior partitions, windows, and cladding. The building system uses layered assemblies of EPDM membranes, PIR, and PUR insulation, cement-bonded boards, and vapor barriers to improve thermal efficiency and airtightness. Modules rest on point supports, reducing foundation time, and can resist wind speeds over 170 miles per hour. Factory production cuts material waste to 5 to 7% and lowers CO2 output by up to 45% compared to traditional methods. This approach reduces site labor and speeds up timelines. Overall seems okay, but this method might bring troubles with transportation. Moving large, fully built modules requires special logistics, which can increase costs, limit design dimensions, and complicate delivery depending on the location. Next, we have some staples that reinforce and stabilize concrete or brick surfaces by stitching across damaged areas. The company says they come in different sizes. They're sold in packs of 5 or 10, depending on the model. 3 is labeled for use in cracks that are between 0.04 and 0.2 inches wide. The measurements likely describe the size of the staple itself or the space it covers. These staples are used to fix cracks in materials like concrete or brick. To install one, a small groove is cut across the crack. The staple is placed so that each side goes into opposite edges of the break, and then the area is filled with something like mortar or epoxy. When everything sets, the staple helps hold the surface together and keeps the crack from opening up more. This follows a method already used in the construction field called crack stitching. What seems to make them work is the combination of physical anchoring and the bonding material around them. When everything is applied properly, the result is a stronger repair that can handle some movement or stress. And the number of staples and how far apart they go depends on how long and wide the crack is, and how much weight or pressure the area takes. This system is designed to solve a common challenge in construction: how to connect parts of a building that stretch from the inside to the outside without losing heat transfer. It uses a layer of insulation, usually polystyrene, along with steel reinforcement bars that pass through the insulated core. The insulation is usually between about 2.4 and 3.1 inches thick, but it can be adjusted to suit different building needs. Special inserts are added in key areas to keep the structure stable and prevent the insulation from getting squashed. It's commonly used where balconies, overhangs, or other projecting parts connect to the main structure. These connectors help keep the building's insulation intact while still allowing those parts to carry weight and force safely. Depending on the project, different versions are available for connecting concrete parts, steel beams to concrete, or even steel to steel. There's also a version that adds extra fire protection, using stone wool layers to meet high fire resistance standards. From an engineering point of view, the steel bars inside the unit tie into the building's own reinforcement system. This allows them to handle all the forces that act on a structure, including pulling, pushing, and bending. Design instructions are provided to help engineers plan exactly how the system should be used, including details on how to size and place the reinforcement. The product meets European standards for safety and performance and is used in many projects across the continent. It's especially useful where energy efficiency and reducing heat loss are important. Construction includes various methods that ensure durability, efficiency, and aesthetics. From building with bricks and concrete to using wood and metal structures, each technique has its own importance for strong and long-lasting results.